So hi, my name is Mithun. Now that you're done reading my great joke, the XKCD famous joke. So great, when exactly you need it, it stops working. Great. Okay, so I'm going to present on a topic which we have been thinking about working on, and we call it like our neural networks learning spurious hidden patterns. So quick agenda of what we're going to do today. The first 5 minutes or something, I'll probably explain what the terms included in the whole work are. Then we talk about what the problem is, a bunch of solutions we came up with, the results, and a bunch of future work we are planning for. Okay, so start off with, we are working on something called natural language inference. So this is a small specific task in the big array of natural language processing tasks. So what is natural language inference? Or in this case, the big question people asked a couple of decades ago was, what kind of a thing is the meaning of a sentence? If you're given a sentence, what do you mean by a meaning of a sentence? Or they came up also with an evolution, after an evolutionary perspective, they came with the sentence, a new question that, what concrete phenomena do you have to deal with to understand a sentence? I have no idea what that says, but.
You can ignore it.
Okay, so the answer to that was to understand an entire sentence, it's a collection of tasks, subtasks, which we need to look at. If there are linguists in the room, they will identify a bunch of the words here. One of them in this case is lexical entailment. So this is just FYI, you don't need to know any of these things. I'm coming back to the definition of the task which we particularly focus on. It's called natural language inference, also known as recognizing textual entailment. So what is it? So basically, recognizing textual entailment means if you are given, apparently, two sentences. They call it a premise and a hypothesis. The first premise is, I'm not sure what the overnight low was. And the second sentence is, I don't know how cold it got last night. So if you or the machine is given these two sentences, it is supposed to pick up one of the three labels, which means the labels are entails, contradicts, or neither. Usually it's called neutral. So in this case, the label is entails, by which what we mean is, given the first sentence, the second sentence entails from the first sentence. So essentially it means the same thing. It's like two people saying the same thing in two different ways. So this was one of the subtasks people had identified like a decade ago and said, okay, this is part of the big natural language understanding process. It's also known as recognizing textual entailment, coming from the word entail. Formal definition, we say T entails H if typically a human reading T would infer that H is most likely true. A human reading the first sentence will infer that the second sentence is true. So that's a formal definition. So coming back to the whole idea of how to solve the problem of natural language inference, Stanford, a couple of years ago, came up with this huge data set of around 400,000 pairs of entailment questions where you have a text and a hypothesis, and the machine was supposed to categorize it into either of the three categories. For example, if you look at this, this one, a soccer game with multiple males playing, and the hypothesis is some men are playing a sport. So the machine is expected to return you the label entailment. Similarly, if you look at a black race car starts up in front of a crowd of people, and the second sentence is a man is driving down a lonely road. So it's a contradiction because the first sentence has got nothing to do with the second sentence. So they came up with this huge data set of collection of sentences, and this became a leaderboard or a collection of how people can beat the latest scores. So just to give an idea, right now it's at 91.6, which is very close to the human performance. that is test accuracy. So essentially, people have been like across these years, starting 2015 till 2019, trying to come up with neural network models where the model is trained on a bunch of sentences initially, and then as a test, you give them another collection of pairs of sentences, and the model tells you if it's neutral, contradiction, or entailment. So this is all like FYI kind of scenario. After the previous data set, the Stanford Natural Language Inference came out. 2 years ago, 1 year ago, in 2018, Samuel Bowman, the same person who created the Stanford Natural Language Inference dataset, came up with a new dataset called multi-genre NLI. The only difference here was that it was very similar to the same set of pairs, except in this case, they divided it into a bunch of categories. So they got fiction. They got a bunch of fiction novels and things like phone conversations, face-to-face speech, and they categorized it all into separate genres. And the idea was that if you can train on one of the genres, can it be transferred across another genre? So, for example, here is an example. The new example in the new multi-genre NLI was, so this is like somebody, it's a phone conversation. Yes, now you know if everybody, like in August when everybody is on vacation or something, we can dress a little more casual. And the hypothesis is August is a blackout month for vacations in the company, which has got nothing to do with each other. So the machine is expected to give you a label of contradiction. So yet another example, premise in contrast, the suppliers that have continued to innovate and expand their use of 4 practices, blah, blah, blah. And the hypothesis is the suppliers that continue to innovate in their use of the 4 practices consistently underperformed. So here, underperformed as opposed to outperforming, it's a contradiction. So the machine is expected to give you the answer contradiction. Again, the same story continues. There was this leaderboard, shared task, where people all around the world compete for this. And the highest ranking was 74.9%. And this is from Chen. And then this was a model called eSIM. Again, you don't need to know any of these things. Why I'm saying all this is, so the question is, okay, why are we seeing all this? What is a big problem? If things are all working fine, if all these neural networks have been learning all these things very well, why do we care? So this paper, Gururangan et al. And a bunch of papers after that, came after this multi-genre NLI was published. And they came up with this thought experiment first. They said, hey, for the humans first, I'm giving you a sentence. In this case, the premise, someone is not crossing the road. And the hypothesis, I'm not giving you a hypothesis. So they asked the human, OK, can you pick a label from one of these 3 things? The human immediately says, no, because the whole task is that you need 2 sentences. Right? Given 1 sentence and a second sentence, generally can I come up with either of the 3 label classification? So the human fails there. Surprisingly, what they did was they took this whole MNLI data set, throughout all the hypotheses, picked only the premises, took most of these top ranking models, trained on them, and guess what? All these models can do well on NLI data set without even looking at the hypothesis, which means the neural network had no idea that there were 2 things called premise and hypothesis. It just looked at 1 sentence, and still it was able to do as well. So let me throw some numbers at you. So these are 3 top performing models. This is decomposable attention, eSIM, and DIN is this thing. So this was the first data set I was talking about, the SNLI. For comparison, in 2019, the top ranking was 88.9. And then the same model gives you 86.5 without hypothesis. So which means the neural network really was not comparing 2 things. It was just memorizing a bunch of things, saying that, OK, maybe when I say not crossing, the label is entailment. I don't even need to know what the second one was. For comparison, this was SNLI. This was the state of the art in SNLI. This was multi-NLI. they just tried it with just premises, and for comparison, 74.9 was a state of the art with this paper, and they just got 72 without the hypothesis itself. So this was a shocker for people, which says, what is a neural network after all learning? I mean, if you guys are familiar with neural network, the whole concept of interpretability is that we don't know what the neural network learns. It's supposedly learning something, and we call it a black box. But this was like a counter argument, or they just debunked the whole myth of neural networks, saying, it probably is not learning what you think it's learning. Ideally, you need 2 sentences to get the label entailment or contradiction or neutral, but apparently the neural network does not need it. It still does fine with just the premise and not the hypothesis. Okay, so then they tried it out on a bunch of different data sets. You can see that this color, I don't know what color that is, purple, I'm colorblind, so blue, purple, whatever. So most of the time, like these things, like if you just predict the most frequent class, it's doing as well as the trained hypothesis model in most of the cases. So this is like further experiments on other similar data sets, and all they were trying to say was that, you have great neural networks models, apparently they are doing great, but hey, they still will do great even if you take out half of the data. So just letting you know that so far we were covering the definitions, and then we talked about this MNLI issue. So why are we talking about this? Like, where do we come in from University of Arizona? So while this thing was happening, like in the world, we were here in our lab, we were parallelly working on something called a fake news challenge. So this was like 2 years ago when there was a worldwide competition called Fake News Challenge, where the idea was, if you are given a headline and a body, just like a news article, can you find which one is fake? Is the headline fake or the body fake? The idea being that if you say, for example, you suddenly see a spurious article, okay, and you think that this is fake, but you don't really know. But what you can do is you can go to one of the reliable sources, Reuters or BBC, and then let's say find a corresponding headline for it. Now the idea that people came here was that if you have a headline and a body, and if you can now classify them into either of these classes, like similar to what NLI was doing, natural language inference, that if a headline agrees with the body, and if the headline came from BBC, then we can say that the body also is reliable. Doesn't matter where the body came from. And vice versa. If, for example, the headline came from a spurious, you think it's a spurious data or a news article, whereas a similar article from BBC ends up being disagreeing with it, it means that it's a fake news, because when compared to reliable source, the comparison is falling into disagree category, which means it's contradicting each other. So 2017 is when a bunch of guys came up with this whole fake news challenge, saying that, okay, why don't we use the same concept of recognizing textual entailment into the whole comparison of headline body, and maybe using this way we can identify fake news. So, and the whole idea was that either you first classify it into unrelated. If it's unrelated, you can just stop and move on, because if the first thing is talking about Barack Obama and the second one is talking about bad child escapes, I mean the headline is talking about Barack Obama and the body is talking about bad child escapes, it's unrelated, stop, doesn't matter, move on, go to the next data point. But if it was related, then do categorize it into either of the 3 categories. Also, I just still want to mention that this is same as the hypothesis. Like, for example, headline becomes hypothesis and your body becomes premise. And the 3 categories earlier we saw was entailment, contradiction, and neutral. So they just call it agree, disagree, and discuss. So at that time, so this is again taken from the same Stanford natural language inference data set. In 2016, when that competition came out, this was a state of the art. It's called decomposable attention model. And we used this particular model in the fake news challenge. And if I can quickly explain what an attention is. Attention is a concept where in neural networks, again, going back to the whole concept of, people had neural networks and people said, okay, it seems to be doing fine, but we don't understand what is happening internally. So this guy, Parikh, it was actually, so this is a new natural language processing equivalent of attention, but before that it was invented by Danu for the vision problem. Anyway, the concept here was they came up with this matrix kind of layer in a neural network, and then they said, okay, so here is the hypothesis and here is a premise. If given these two sentences, can we find which word does the neural network give more importance to, also known as more attention to? So in this case, the first sentence is, in the park, Alice plays a flute solo, and we call it a hypothesis. And here's a premise, someone playing music outside. Once they started adding the whole attention layer, they saw that neural network was giving more importance to Alice. Given Alice, they think the word someone is relevant. Given place, they think the neural network thinks the word playing is relevant. So this was the whole idea of adding attention to sentences so that we can kind of use a magnifying glass and look into what neural network is doing. So this was a big thing in 2016, and people said, oh, this is a great idea, the decomposable attention, that we can decompose the sentences into finding a given word, which one does the neural network think is important. So we used this particular neural network, and we ended up in rank 5 out of 135 worldwide competitions. We had an accuracy of 92.89. So things were going great. We were doing pretty well in natural language inference, especially in the fake news challenge. We published and said, oh, hey, we solved the fake news problem. So a year later, right, so we are coming back so remember, we are parallelly working, those guys were working on this data set called MNLI, and we happened to be working on this. Again, we didn't know things were existing at that time. In next year, the same guys came up with the next version of fake news challenge called fact verification challenge. Now, how is this different from a fake news challenge? This was the part in the first year, which was given two sentences classified into support, refutes, not enough info. Again, the same thing as contradiction, entailment, and neutral. However, they added one more layer saying, okay, right now we are not giving you a headline and a body, but instead all we give you is one sentence. You have to go dig up relevant documents in Wikipedia or reliable news articles, come back with a bunch of sentences, and then you do the same part which you were doing earlier. So they call it like, for people who are familiar with natural language processing, this was the information retrieval part. And this is where you combine the evidence, which is, in this case, remember, this was given a hypothesis, find me a bunch of sentences from Wikipedia which is relevant, which we think is relevant to the given hypothesis, and then you classify them into a bunch of categories, which we saw already. So, for example, they said, okay, the claim, the Rodney King riots took place in the most populous county in the USA. So you, or the machine, was supposed to go into Wikipedia page, find the Wikipedia page for Los Angeles riots, and then look for the words Rodney King riots. Oh, this exists, or maybe it's therefore the whole thing is relevant. So the machine is supposed to say, let me pick the whole paragraph. Oh, by the way, I don't know if Los Angeles is the most populous county in USA. So now you need to go dig in again and find if Los Angeles County is the most populous county in USA. Return these 3 sentences. Given these 3 sentences, now we plug in the other part, which is divide them into supports, refutes, or not enough info. Again, this is what I was saying. There are a bunch of terms which are equal to each other. Hypothesis is same as claim as headline, which Every single data set calls differently. Premise, they call, some of them call evidence, some of them call it body. Labels, agree, supports, entailment is same, disagree, refutes, contradiction is same, neutral is same as discuss. It's just author, how the author wants to call it. Okay, so coming back to the story, so we were really happy. We had a great performing model. We thought, okay, so the only other part we have to do is get this particular information retrieval part, plug in the already existing model, and we are probably going to win this particular competition again. So the idea we thought was, we already have a trained model which was trained 1 year ago in 2017 on the fake news data set. And this is pretty similar. If you go back and look at it, like this is also a bunch of sentences, which is very similar to your headline body concept. We have a body. Our neural network was doing really fine. There is no reason why we have to completely retrain the whole thing. Why don't we take the already trained model and use it there? Great, really happy. What was the problem? We ended up last. In the whole thing, we ended up last, in this competition. So this was a little confusing to us, right? So why did the previous model, which worked really well in our first competition, fail miserably? We had 37% accuracy while the first team was 67%. Also, we must mention that, remember, the idea is that we are not taking the neural network model and we are not retraining. We were just saying, OK, let's take the same model and try using it directly into the new data set. If we were retraining in the new data set, probably we could have got a higher accuracy. But we said, OK, this was one of the experiments we were performing. We did not retrain. We said, if we already have a trained model, which was trained on very similar data set, fake news, fact verification, Wikipedia pages. So there's no reason why one should not work in the other. So this was a little confusing for us. So instead of blaming the poor grad student for writing bad code, which is me, which, believe me, is most of the cases when something goes wrong, it's me, we also decided, let's dig in and see what is going on. Let's dig into the data set, and let's see what is going on. That's when we ended up finding something what we call the Ben Stiller effect. So what is the Ben Stiller effect? When we went through this whole data set, we realized that the occurrence of the name Ben Stiller is associated with the label agree in more than 70% of its training instances in the training data set. So remember, we have a state-of-the-art model. Everything is fine. We think neural network is the next big thing after canned beer. So everything is fine, except when we look at the data, wait, this rang a bell. It's like, this is not right. Why would what if the neural network is actually just looking at the word Ben Stiller and seeing that every time I see Ben Stiller, the label is agree? We dug in more, and to our shock, we find that Israeli Americans, like Ben Stiller, 74% of the time that Ben Stiller occurs, the label is supports. All the time when the phrase Israeli American occurs, the label is supports. Every time that American author occurs, the label is supports. So maybe that's all the neural network is doing. All it's saying is, hey, whenever I see the word Ben Stiller, I'm going to just throw a label agree. We don't know what is happening. That is a big problem with neural network. We call it the big interpretability problem. Maybe this is what it is learning. It's just learning the spurious underlying statistical facts like this. So this is the key question we asked ourselves. Is the model overfitting on Ben Stiller effect, what we call the Ben Stiller effect? And for the uninitiated, overfitting is a very nice way of saying, is the model memorizing just words or spurious patterns? So now then we ask the question, how do we verify this? Can we just find a way to do this? And thankfully, to our help, we were actually using the decomposable attention, which means we already had a tool inside our model which was pointing us to combination of words. Given the word Alice, I give importance to someone. Given the words place, the neural network gives importance to playing. So if then by extrapolating this, if our hypothesis was true, every time it sees Ben Stiller, it must have thought, it must have learned something or given more weight to it. So this is what we thought of, like, is the model overfitting? If yes, how do we find it? So we said, OK, let's train on domain 1 and test on the same domain. Test on domain 2. So in this case, OK, this is, yeah, cross-domain is, say, for example, we train on the fake news challenge data set. We test on fever data set. So at the same time, we train on the same data set, fake news, and we test on the same data set. The idea we were thinking was that if it was overfitting, if the neural network was memorizing, then the overfitted words will receive high attention scores when the cross-domain model makes an incorrect prediction, and low attention scores when the in-domain model yields the correct prediction, which means it is relying on Ben Stiller. It is throwing in a huge weight behind the word Ben Stiller, and it's saying, oh, agree. I don't care. I'm not reading anything else. I'm just looking for the word Ben Stiller, and I'll just say agree. Remember a couple of slides ago, the other guys, when they were doing with the other MNLI data set, they just took the headline, or in their case, premise, threw it at the neural network, and it still was giving you agree. So we didn't know that research was happening there. This is where we were thinking about this. And so we said, OK, let's find the weight of attention weights. Top 5 words when out-of-domain model got the prediction wrong, but were not there when an in-domain model predicted correctly. Simply means when it's making mistakes, is it memorizing something? As, in, was, by, lot of stop words as expected. However, this shocked us. Film. It's giving more importance to the word film whenever it's getting things wrong. Why is that happening? So then we started plotting the whole list of words which were, which it had given the maximum importance to. More than this, we categorized it into a bunch of part-of-speech tags. So for people who are not familiar with part-of-speech tags, all we are doing is we assign a bunch of letters or tags. For noun, it's NN, a plural noun is NNS, proper noun is NNP. So we started categorizing them. We said, OK, let's see if we categorize based on the POS tag, the part-of-speech tags, which one is highest. So we found out, OK, IN is highest. IN is preposition, which means the machine is giving way too much importance to the prepositions. And then second is NN, nouns, which is not really a good thing because Ben Stiller is a noun, right? So American author is a noun. It shouldn't really be caring about these things. We said, OK, still probably we are wrong because the first one is IN, which is prepositions. OK, it still is thinking, Ben Stiller is an actor. So therefore, probably it's giving importance to the word is, and it's doing fine. That is when we realized VBD, verb in the past, VBZ. So we realized we were actually categorizing it based on all this standard part-of-speech tags. Instead, we thought, OK, why don't we cluster them together and put all the verbs together, put all the nouns together. Like if you look at it, there's in part-of-speech tagging, there is NN, NNS, NNP. Ideally, all of these is just nouns. We can all categorize just all of these into NN star. OK, we said, let's see what happens when we do that. Boop, stops. Great. When you really need it. What just happened? OK. There you go. OK. So when we categorize all of them together, the neural network is giving maximum weight to nouns, which is not right. It's not supposed to learn on Ben Stiller. It's supposed to learn Ben Stiller is an actor, and Ben Stiller is not an actor. Is an actor is what it's supposed to learn. It's not supposed to learn the word Ben Stiller and give more importance to it. It's not supposed to learn American author. It's supposed to learn the whole sentence and the underlying semantics, or why, once given one sentence and the premise and the hypothesis, what is linguistically causing these two things to be entailing or contradicting to each other. This was a big shocker for us because it's giving us, like, the IN was overtaken by NN, which means like all these guys, the nouns were given the highest importance. Now, great. OK, so we found the problem. Now, how do we mitigate this overfitting? Is there a way by which we can actually fool the neural network into learning the right thing? Right? So fool as in like we don't want you to focus on the nouns. So thinking about this, we came up with a bunch of solutions. This is a concept called knowledge distillation. Comes from Geoffrey Hinton's team. Geoffrey Hinton is considered the big father of neural networks. I think he even won the Turing Award for inventing the new neural networks. So our idea was, what if we replace the words or phrases that are likely to cause overfitting with more general information that aims to preserve as much of the text semantics as possible, right? So ideally, it doesn't matter if it was Ben Stiller. It could have been, Jim Carrey is an actor. Ben Stiller is an actor. The neural network is supposed to understand the is an actor part, not the name part. So this is the whole idea which we are saying, OK, even if we have a model which was trained on one domain, it should really be able to evaluate on a very similar domain. In this case, remember, it's very similar. It's not like, this is science and this is politics. This is both fake news. For example, like it's all text from Wikipedia. So really, they're all like, we can say most of them are politics, for example, or geography. So they're all similar domains. A trained model trained on one of them should really perform well on the other one because they are very similar domains. But unfortunately, it fails, as we just saw in the previous slides. So this is a setup which we are trying. Can we come up with some kind of a solution which works all four ways? It should work in domain for both of these. It should work cross domain also. OK, so this is where your basic, like initially when you had a claim and an evidence, this is what we were feeding into the machine. For example, with Singapore Airlines, the Airbus A380 entered commercial service. And the evidence was the A380 made its first flight on 27 April 2005 and entered commercial service on 25 October 2007 with Singapore Airlines. This is one of the claim evidence examples. OK, so this is what we were feeding into the model. Now, the first technique or method we tried was, what if we simply delete these words? Like, if you think it's relying on Singapore Airlines or Ben Stiller, let's see what happens when we just take these words, nouns, simply delete them, with nothing, the dash, the Airbus, we remove the Airbus, entered commercial service, A380 was also removed. Here we removed the key factors which we thought the machine was relying on, dates, Singapore Airlines, all of this. This is one of the techniques we tried. Second technique was replace the named entities. So named entities usually are, so the concept of named entity is that given a sentence, you can classify them into things like organization. Singapore Airlines, there's a named entity tagger from Stanford or many other places where they say, given a sentence, I can tell you this is an organization. This really should be organization. I don't know why they call it miscellaneous. This they find as a date. So again, the first flight, the word first, they call it ordinal. So this is just a whole concept where they take the whole bunch of sentences and rename it with the corresponding named entities. OK, we said, OK, let's try this one also. We'll rename this thing Singapore Airlines with organization, whatever. We're just going to feed this into a classic NER tagger, and let's see what happens. Second technique. Third technique was we do the same thing as an NER tagging, but instead, we are going to explicitly point out to the neural network that organization C1 also exists in evidence, which means we don't care if it is Singapore Airlines, Malaysian Airlines, Lufthansa, it's an organization C1. We want the neural network to ignore the whole concept of Singapore Airlines and focus on the fact that it occurs both in claim and evidence. And this was the idea we were trying to force feed the neural network, a little bit of cheating the neural network into believing that ignore these things. We don't want you to focus on this. Focus on the underlying semantics that given these two sentences, can you come up with a good evidence? So this is what I was saying. Like C stands for claim. C1 means it occurs first time in claim. It also occurs in evidence. So we are like explicitly pointing it out. One more technique which did was, great, I have a to-do left there. OK, I hope we have a conference happening in Hong Kong 2 days from now. I hope the guy who is presenting it is changed this. I can get away with it here, but not in Hong Kong, I hope. So we went one more step ahead, and we call it supersense tagging. So this was the next level of tagging, where they say motion. Entered is replaced with motion. So these are all well-known taggers that's available on the internet. Like we call it motion. Entered is motion. 380 made is called stative. So this is a little more granular level of NER tagging. So we use this also. OK, so let's see what happens. We tried it both on in-domain and cross-domain results. First, in-domain. The idea is that, remember, like if this has to work all the 4 ways. Within the domain, also, we need it to do well. If it is not doing in the domain, it really doesn't help that it works only across the domain. Good news is, the lexicalized, what we call lexicalized is the plain text we were feeding in. Most of the other 4 models do as well as the lexicalized model in domain. So the first part is solved. OK, the model is doing fine, even though we kind of manipulated with the data using deletion, overlap aware, or supersense tagging. Let's see how it does across the network. So across the network, we should point out that the lexicalized model does really poor across the network. That's what our whole problem was. We failed the whole competition because when we took the same trained model, used it in a new domain, it fails miserably. However, the deletion, when we just took out all the deletion, just to delete the NER tags, it performed even worse than that. But look at this. The overlap-aware model actually does better than the lexicalized model when it is taken across the network. So what happened? So I mean, if you see this like the overlap-aware, the NER plus supersense tagging, too much granularity is what we call, right? So this was probably like the Goldilocks zone where we said, OK, at this point, if we simply call it, so the method which worked gave us the best result was this one, where we are just calling it C1. Instead, if we had, when we went a little more deeper, it failed. It says, OK, oh no, too much data. I don't want that much data. It's going to fail here. But apparently, just the C1 is doing pretty well. It's actually beating the lexicalized model across in the cross-domain tests. So what did we learn from this? What we learned was, if you use this kind of a technique, you're replacing Stiller with person C1, it actually learns and preserves, right? So whenever the original label was agree, it is preserving the label. But this was our problem, right? So here, the original label was disagree. The machine was predicting it as agree. In our case, when we use our technique, it's getting the label correctly. So it can preserve the context, did not place importance on Stiller. So there's no more Stiller here. This is like the key, the attention word. It's not there because true is underdog. So it doesn't exist there anymore. In the Ben Stiller example, previously it was thinking Stiller is important. Whenever I see Stiller, the label is agree. Remember? Stiller, agree. It was blindly predicting it. When we took that away, looked like it is focusing on the real sentence, the underdog. Probably that was the whole reason, the true underdog story or whatever the combination was. It seems to be like focusing on the right things and not, it's like a dog. You should want the attention to be focused on the right thing and on, which is you and not the cat running around. And this also evidently improves the predicting the correct label. So here, this is just numbers. All you have to look is 24 instances were wrongly predicted. In our case, 19 switched it back. So like more than 70% of the time, we are getting it right. Like earlier, there were 24 of them were disagree, but we got it right in most of the cases when we were replacing these keywords with whatever the person see or organization, etc. So conclusions, what we did was we went through the importance what neural networks place on lexical items, proposed a bunch of semantically masking word classes. We are not saying this is the best way out. In fact, this is definitely not the best way out because we don't have great accuracies. We are still like close to 50s and 60s, whereas this was actually 80s in domain. But there is hope. We just want like a vanguard kind of an idea, throwing it out there saying, if you can come up with more smarter techniques of modifying the data, we probably can get this higher up. And that way we will have a model. You train on one thing, you don't have to retrain on when you're moving into a new domain, similar domain at least. And then we can just directly use it because for those of you who are familiar with neural networks, retraining is at least anything between 4 to 12 hours. And you don't want that. If you want to just keep jumping from one task to another, and if you really have a trained neural network model, that's your silver bullet. You just can take this and reuse it in the new domain. So this is what we call as distillation. The whole concept of distillation comes from we relied on distillation. It outperforms model by over 10%. Again, not great, not the best thing we could ever invent, but we thought, okay, it's like a good thought towards the whole idea of what is neural network learning after all, right? So there are some things which we have been working on is this is called MED-NLI. So this is a natural language inference for clinical domain. So can we come up with a model which was trained on news, politics, and directly use it for this kind of setup? Sentence 1, same thing as your claim and evidence. Labs were not notable for CR 1.7. And this was actually created by doctors. Sentence 2, patient has elevated CR. I have no idea what this means, okay? But the machines should still do well. That's the whole point. Because even if you are moving from politics to medical or whatever it is, the underlying semantics or linguistics really doesn't change. These two sentences, they are entailing each other. Like I said, the doctor knows and the machine should know. We humans should not really care because the machine should have learned the underlying semantics. Why, given one sentence, the other sentence entails from this. This is an architecture which we are thinking of. This is based on a mean teacher-student architecture where you have a hand-holding kind of model. I can explain this more if you're interested. This is now the big thing. I don't know if you're familiar with this whole concept called BERT. Like Google came up with this whole data set. Not data set. It's a, I don't know, embedding-based, whatever BERT is. So apparently there have been comments that, is it learning spurious statistical clues? So this is what we have been, like, we are creating a table like this. We are taking all the state-of-the-art models, BERT, eSIM, all those things which really did well in the other tasks, trying it on MED-NLI and trying out our NER tagging and checking. We are trying to fill up this whole table and see what is going on. Our hope is that even if we don't, even if the current technique is not doing great, at least we'll understand what happens when the state-of-the-art models is actually faced with overlap-aware NER, or where we just take out the whole keywords. Do they still do well? If they don't do well, which means they were simply memorizing the whole thing top to bottom. This is our holy grail. We are, like I said, if I can train something on fake news and then I can test it on fake science. For example, if the machine comes up with an article that Earth is flat, can we raise a red flag and say, that is not right? Because I learned from the fake news, I learned something. I, as in the neural network, learned some kind of an underlying fact. I went into Wikipedia, dug up, and found that Earth is not flat. The machine can do it by itself. And if we can raise a red flag, so much for our new fake science that is floating around since days. Okay, so stand up and fight back for science, which is where we are from the College of Science, so at least we should do. Okay, last dedication. This is from yesterday night. My dog, I promised her I will go do trick or treat. She was dressed up for this. And she was really pissed off because I was working on this slides. So she said, okay, as long as you put this up, no animals were harmed. Like, I was harmed. I didn't go out for trick or treat. So if you can put that up, you're fine. Okay, that's all I have. Thank you for your attention. Questions? Yeah, sure.
Is the idea over time that you can't be 100% accurate, but if your accuracy gets better, that we could flag things that, say, online news items that, you know, even if you're only 80% accurate, if it gets flagged, it can be reviewed? Is that the goal?
We really don't want to call it a binary classification, saying that yes, fake or no fake. We were thinking of presenting like a heat map, saying, you know, we think this is towards a fake side. We are leaving it to the user discretion. So the idea we were thinking was, you know, these days everybody has a smartphone, but we probably don't have access to real knowledge. We have a bunch of contradictory knowledge. So every time the kid or a new student who's seeing an article, you know, if it raises a red flag saying, you know, the scientific community thinks it's probably spurious, up to you if you still want to believe on this or not. At least that we feel is like a starting point towards, you know, raising a red flag, telling people, you know, everything you see on the internet is not true. You might want to go to school for a change. So yeah, that's the holy grail. I don't know if we will get there, but that was where the idea was.
Is this with Chris Impey? I know he's in.
Yes, so the whole idea of retrying it with fake science was, we were having a discussion with Chris Impey. He is collecting his own data set. So we thought, okay, we'll take a step back. We'll come up with a solution. So our next step is actually to get his data set and work on it with him. So yeah.
I think it shows promise.
Yeah.
So have you checked the vocabulary difference between the first dataset and the second dataset? And assuming, because in general, the vocabulary difference will affect the cross-domain performance. So when you replace the named entity tag, I mean the semantic class with the named entity, you basically reduce the vocabulary difference between the first dataset and the second dataset. So have you checked that?
That's a very good point. I should really check that. And also a similar thing which we were wanting to check is how much of a given a bunch of vocabulary, how much is the bias in the data set that happens. So like if there's a lot of, you know, inherently there is a lot of, you know, bias towards a bunch of news articles, or depending on how you get the data set too, right? So these are some experiments which we have definitely had in mind. That so the answer to that is, the first thing is we'll actually try it on an entirely different data set. And if the same thing happens, we know that is the reason. We have to go back and check the vocabulary, right? But if it is not, if it's working fine, then probably there is some issue actually with the neural network. So that is an experiment which we thought we'll perform after we go through, you know, trying out all these state-of-the-art combinations and try it out on all these data sets and see if that, I mean, decomposable attention is just one model, right? I mean, we don't know how that was working or learning. If it is still doing fine with doing fine or not doing fine with these other models, then we actually have a problem. So then vocabulary is your solution, right? Going and finding if that was a problem. So yes, definitely things we have thought of in mind, keeping in mind for that.
So what kind of NER tool do you use for your task?
I think we ran it over the core NLP. NER tagger was Stanford NER. I think, you know, processors is there in our lab, and it runs on top of the Stanford NER tagger.
Yeah, for the numeric domain dataset, I mean your future work, I think. So when you're doing the NER for the medical domain, there will be a serious issues.
Yeah.
The drug one, I mean in the support, I mean in the premises, and the drug two in the hypothesis. Even though you identify them as drug, I mean the same drug type, but they not belong to the.
Yeah.
The medical domain is totally different.
No, I agree. So we need to find if there's an NER tagger which is specific for med domain, or if we can identify this. Also, the other thing we have been thinking of is Figer. There's this data set called Figer where it is more specific. It classified things into medicine and not medicine. So maybe once we can send that first, classifies everything as medicine, replace it with the word medicine, you know, and then we can do the NER tagging. Like medicine is a word probably which NER understands, not a particular, you know, CR baseline or whatever that means. So that's a good idea. Okay. Sure.
Kind of naive meta-level question. The space of fakes is unbounded. Is it possible, once I understand your algorithm, I could write some adversarial approach that sneaks around you?
Yes. So the interesting part there was human written fake and machine written fake. So we found that human written fake is much, much tougher to identify because humans tend to use hedging words and beating around the bush. In fact, I don't know if you're familiar with this, there's a village in Macedonia where the entire village wakes up and writes fake news, and they get paid for that. So we learned the hard way that finding those kind of, there are algorithms which, write fake news, and those were easy to beat because the machine was trained on learning this, and recently it came out from Allen NLP AI2 team that they created a fake news generator. You give it a topic, it'll create a fake news for you. So, but those were easy to defeat because the machine has already seen it, so a counter argument can find it that's fake. But human written things were actually difficult. So yes, we don't know, it's an unbound question at that point. Any more questions? Sure.
I have another one about, at what point do you know or do you get a feel that you pulled out all the trigger words that you needed to? So names are obvious, so like pulling Ben Stiller out.
Yeah.
But even something as innocuous like dodgeball.
I agree. So we are going to rely on accuracy. It's a trial and error.
Yeah.
Pull out. Does accuracy increase? No. Go back. Try something else. Go back. So at that point, it becomes an engineering issue than a science issue, which probably neural networks totally is an engineering thing than science at that point. So yes, we are going to rely completely on accuracy of is it doing better. There is, like I said, there's really no scientific explanation to why one would work. Our guess is that this was too granular. Like when we said, like you said, this is an exact example. Like at what point do I know that this was too granular and this wasn't? So we're simply.
There could be bias there against commercial services versus.
True. Yes. So.
Services. There's always some sort of human bias in any of those words until you just get down.
Definitely. So that's why we simply rely on accuracy. Is the accuracy improving? Yes, that's a good technique. No, throw it away, try the new technique. This is what we did in all of these techniques. This we threw away most of the time because this wasn't giving us great results, whereas this was. So we present it in a PowerPoint and show it to people. It works. Okay. All right. Any other questions? All right.
So how many semantic class you use for the name entity?
How many? I need to look at the actual tagger, what the tagger is using. I think the NER tagger classically has 10, the organization, government, things like that.
Yeah, because I was asking that because so the size of the semantic class may affect how you reduce the vocabulary.
This is going back to your whole generalization versus granularity question. Like at what point do you want to make it more class-based? Like this has the second one, artifact and motion has way too many classes. That is why probably we are guessing it is too granular for the machine, whereas this was okay because it was at a higher level. It's okay organization, but don't go too deeper into motion and things like that. So that is probably the answer to your question that, too granular is bad. That's why I was talking about Figer. That's one of our next experiment. That is more like somewhere in between this and that. So like medicine, for example, if it can recategorize it into medicine. Again, it let hypothesis non-fingo, which means we cannot say what the data is telling us. We just look at the data and say, okay, accuracy is improving, great, we stick to it. Definitely engineering at this point and not science. All right, any other questions? Okay, then thank you. Thanks for coming.